Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Camera Tuesday, we're going to talk about color matching and calibration. So let's dive deep into it. So what exactly is the problem? Well, reality is there is no such thing as color. So many times you see infrared images, it looks like a black and white image. That's true. Then we put artificial color on it, which we call false color. Yeah, our brain is doing the same thing because what's the difference between blue photon and red photon? Nothing. It's just the frequency. So if frequency starts from lower 700s, that's like around red color, and then it goes to violet, and then it goes to ultraviolet, then it goes below basically infrared. So inherently there is no color, quote unquote. All it is a photons of different wavelength. What we call color is our brain's tagging data. It's a metadata on a thing that we are observing, so to say. And problem with that is that there is infinite combination, and not to mention because of some limitation of our eye, we truly do not, even in this band, so to say, we do not observe all of it. Yes, we are much luckier than many other species who have only dual data array. We have tri data array, as in like 3 cone cells. So we do have better perception, but still very limited, because the where exactly a wavelength can be, well, it's a continuous thing. So anywhere we divide it in, like, 3 units, red, blue, green. Somebody can divide it in 6 units, somebody can divide it in 25 units, somebody can divide it in 50 million colors. All would be valid. So that's the issue. And on top of that, there is ratios, because you may have a light source that is giving proper blue light and, like, spectrum sort of blue, and then some little bit of yellow. What is the ratio? Well, infinite. What kind of ratio can be infinite? So inherently the amount of colors, quote unquote, realistically exist in this wavelength is odd infinitum. Do not try to calculate it. So our eyes, basically these puppies, they do their best to separate them. That's the easiest way our eye can figure it out. It's like, okay, what's happening actually, so to say. So it has basically 4 tools to take care of it. Tool number 1, rod cell, on or off, and what is the intensity. This is our black and white sensor. This is how we can work in very low light and still make out things. And this puppy is responsible for, to some extent, motion calibration. So we can figure out things moving very quickly. Thank you, rod cells. Then we have detail layer, that is cone layer. Now cone layers have 3 structures. One is long, another is short, another is basically medium. So basically long puppy is for red puppy, and then you have medium puppy for green, and you have short puppy for basically blue violet. And this is the structure design. Now unfortunately, somehow our evolution really did made a basically front side illuminated sensor. We do not have BSI in our eyes. What does that mean? That simply means light comes from this side and sensor is here. Now like, wait a minute, what are these wiring? If you ever wondered like why the heck we have blind spot in our eyes, that's the reason, because wiring is on top of the sensor, and that's why we do not have very high sensitivity. Like the same cone and rod cell, if you can invert it, like genetically, let's say you engineer a super baby, that these cone and rod cells are on the front side and all the wiring is on the back, that puppy will never have any blind spot, simply because, well, all the wiring just goes out from behind. It does not have an issue. And because it was much closer to the actual retina layer, basically screen layer, so to say, where the actual projection of image is happening, it would be exponentially more brighter and much more crisp. Everything would be exponentially better. Yeah, so that's a really messy thing. Like, they did not had a conversation with Sony engineer who developed BSI sensor. We really need BSI engineering on this. So yeah, that's literally where light comes from this side, but our cells are here. It is what it is, what we can do about it. But all it does, like this puppy is basically con and road, they create a data sheet that our brain interpolates, and based on that we figure out our best to resolve and discern. Resolve simply means what can we see, and discernation, what exactly are we seeing. That's why we have 2 data sets. Color data set allows you to understand like someone's skin, like you can look at someone's skin and like, dude, that person is healthy or sick. And basically rod cell is like motion. I got you, fam. Rod takes care of both of these data go together, and that's why this is the exact reason why we have 422, 420, because we know for a fact that luminance component of an image is much better. Why? This puppy, rod. Rod is very sensitive. Now all 3 components that you have, basically red, blue, green, they are not equally powerful, meaning as in the amount of cells is not equal, so to say. So this is the most realistic description, so to say, is out there. Now you may see many images something similar to this, but it all would be same. That's equalized image, but many times people think that's how our eyes work. No, that's not how our eye works. Anybody who had looked into a Bayer filter array would have figured it out. It's like it has twice the green. Why? In terms of the cells that are specifically medium size and it grows in our eyes, it is exponentially more, so it's far more sensitive. That's why we can easily see green lasers. We are very sensitive in green. Like green, if you have 1 watt of energy pumped into a green spectrum, we can detect it much further away. If you had the same amount of energy dumped into red spectrum, we'll see it almost like the gap is there, but like it will appear a bit dimmer. Blue, yeah, super dim. It will be like no. So that's why and this is the reason why we have green screen. Now like, wait a minute, what? Yeah, because of this structure, that the fact that we are very sensitive to green, engineers, when they were designing the bare array, they figured it out. Hey, we're gonna have red, awesome. We're gonna have green, awesome. We're gonna have blue, awesome. Hey, this does not tile. We need to tile this puppy. So what we're gonna put in the blank space? Some figured out, it's like, hey, just put a blank stare. But they're like, yeah, the color calculation becomes far more complex. So there, somebody can be like, hey, our eyes, green, put green there. So we have green, blue, red, green again because of this. And that's how we tried it. Be mindful. Do not think about this like it's a random thing. We tried every other. It just looked ugly to us. Why? Because it was not matching how our eyes were perceiving it. So it always felt the camera is broken, so to say. So everything scientifically, this thing is wrong because again, our eyes are working wrong. But if you ever built artificial intelligence, we're gonna give them 3 CCD eyes so they can have this equalized, so they can perceive all the colors precisely. We are just like, but again, on low energy, we are awesome. Green cone, and this is the reason why green colors have like much easier way of, if you have green screen, it's super easy to have very sharp borders. Again, its pixel count is twice. And back in the film days, you would notice many of the films were taken in blue screen. Why? Film, the actual chemistry, the silver halide, that puppy was very sensitive to blue. So they were like, hey, blue works best. Now be mindful, inherently all you need is a monochromatic display, monochromatic light, monochromatic, all that. If you have monochromatic, you can figure it out. Generally, green we do in digital, blue we do in film. If you have no other choice, like if the person is wearing green, of course you will do to, you can even have red background if you want to, but generally we don't. It can be done. Be mindful, it can be done. We just choose not to because we have red components in our skin, so it does not work that well. So this is the whole reality of it. Like all of these puppy work together to give us the perception of color, and all we see the colors is just a ratio between these things. How these things are turning on or off, that's giving us the feedback loop. It's like, oh, this is yellow, oh, this is green, this is purple, this is violet, whatever have you. And now we come to the ugly part. No two equipments could be same. Like no matter what you do, you can be like, hey, this is the silicon disk that we're gonna etch basically sensor array. You can take the disk, cut it into like 35mm formats or 65mm if you are going fancy unit. Outcome would be both of them would be different. Like again, subtle difference. We work our ass off to make them as equal to possible, but they will still require calibration if you want to make sure they match each other. It will always be separate. And let's not even go into biology terms, because yeah, everybody sees eyes, like the data communication between their eyes and their brain and their emotional cortex processing of it. Yeah, it's all different, and many people even have this ratio different. Now this is the average of humankind, so if you take a human, most likely it will fall into that, but the ratios could be off. Some people could have green and red bit closer, some people would have blue almost gone, some people will have cone cell just not, like, nope, I'm not working there, relying on rod cells. We call that color blindness. And again, there's 10,000 diseases into it. Look into it if you want to. So reality is, this thing is the best approximation we have at this point in time. So this is all we have to do. Now, why does this matter for colorists or people who are dealing with camera or video or something like that? Is simply because this is directly proportional to our feeling. There are certain shades of red that will, that will give you a good feeling. But just a little bit shade wrong, it will give you a sick feeling. Why? Because again, it may correlate too close to your red blood cell. We do not like to see that color. So there is just like, there is a very narrow line. Certain colors of red lipstick, awesome. Just a little bit off. Just the ratio goes a little bit too on this side. And it's like, no. So it's one of those things, and you would be shocked how much money basically cosmetic makeup company puts into it. I do not want to use fancy word on that. Just makeup company put into that. It's like bonkers. And this is the reason for it. Our eyes are not balanced, and not to mention these ratios are not balanced. Nothing is balanced. Person to person is completely different. And I'm reasonably sure men and women also have different. So this is the problem with colors and all that. Everything is messy, everything feels differently, and no engineer filled this like a BSI sensor and all that. So it's a hassle. So our first line, whenever you are taking a picture and shot or whatever have you, the first line of defense is you have to understand how things go. The first thing is, we have a digital world which has standardization. Now we figured it out. Then on a mathematical level, we can calculate colors. Now here's the deal. That's useless for us because you can get yellow color from yellow, or you can get yellow color by mixing two colors. But it's still yellow. To your brain, that tag, that yellow tag is still being used, even if it's created by spectrum mixing of one spectrum, just like, one sodium ion emission, or it could be like two lights. You have a little bit of red, little bit of green, and yellow. It's like, what difference does it make to your brain? Because your brain can only put that tag into a yellow. Now it does not go inside it. That's why we have spectrum analyzer that goes inside that. Is like, hey, what's the spectrum component? These puppy do not have spectrum component. So all is just like rough tags. It's like yellow, looks yellow, yellow, yellow. Everything is just yellow. So digital world standardized it, and they removed all the redundant data. So you see this sort of color volume, so to say, that's what they are showing you. There is odd infinitum out there, but problem is, not even problem, as in like it's all built for us. Like as in like we are the observer, we are building a standard, it's built for us. So they're like, hey, if human eye cannot tell these two colors apart, or like how spectrally they are apart, as in like, hey, this is yellow that is made out of sodium, this is yellow that is made out of mixing red and green, our eye cannot tell that different. So they're like, why do you want to store two mathematical values? Store one value, call it yellow. So this is how we created a way of compounding all of the digital world. Everything that you see, your digital file, every digital file has this world standardization going into it. How it's interpreting it, that's a different thing, but this is there. This is the backbone of it. So because we have to deal with data compression, and again it goes back to the fact that our eyes have basically far more motion sensitivity. That's why we have like a 4:2 or 4:0, 4 being the basically luminance component, because the road cell must be satisfied. That's the largest surface area out there in our eyes, so that must be satisfied. Okay, you got red. Other things, yeah, you go down. Blue specifically, yeah, goes down. So why the heck we have to deal with that? Because our camera can capture it, like surprisingly well. Our camera can capture it, and if you really want to do it, there was a whole phase between basically going from film to actual current digital. There was a phase where we used to use actual 3 sensors. Now be mindful, that's coming back, because for 8K live streaming of Olympics and all that, you need 3 sensors. Bare calculations are too slow to be done 120 fps real time continuously for hours on end. It's like, just put 3 sensors. And again, for industrial use where you have machine vision, they still use this technology. It's a very awesome technology and cheapest technology to give you absolute color. No, I say this is the red, that means it's the red. It's not interpolation, it's not guessing, it's exact spectrum value. So that data is there in the cameras. Cameras are like, we got this. Problem is that raw data is stupid huge. It's just stupid. The amount of gigabytes, terabytes that you will be generating, it's just stupid for delivery and transmission. So we again go back to this standardization. Take all that data, interpolate it in this volume, and then we're gonna transmit it. So whenever you hear about Rec 709, Rec 2020, whatever have you, that's what you're hearing. It's the interpolation of camera data to what you can show data. So the first line of defense, what does this mean to like a photographer or a videographer, is have a color chart. That's the first line of defense. Why? Well, when you have a color chart, you know, most likely, if the color chart is from brand, you know like what the color chart looks like. Okay, you put it in front of camera, you captured it. Now here's the benefit part. Even if this color is like cheap Chinese brand and the colors are not accurate, it still serves a function. It will allow you to sync multiple shots, especially from different camera, different lenses, and colors will be similar, and you will know if the color is off, because hey, color chart in shot A looks like this, color chart in shot B looks something different. You will know it. And this is something that you can notice, especially if you look at YouTubers, so to say, and they have like low budget scene, they are doing all that, and they have multiple cameras. It's like cuts are very obvious. And it's not obvious because they're cutting it wrong, because they're cutting it perfectly. It's just that the camera A and camera B was not matched, because they did not use this puppy. Like VFX world, this is becoming more and more important, again, because you have CG elements that have colors, and those colors have to match the colors that are in the scene. So put a color checker there. So it's one of those things that is the first line of defense. While you're capturing it, be mindful, your camera has GG amounts of range. Do not worry about the camera. Camera is like, I got this. You have to feed it correct data. So every shot, let's say, take one you're doing, you can have a color checker, then you like take one. Now you do it. So this is the easiest way to make sure all the scenes match up to each other at least. So you can have like a long 3-hour movie and you can have like 50-60 shots in them, and a bit less, but let's say you have that many and all of them match each other. Then you can send it to a colorist and like, oh, okay, I think I can adjust it. If they are all off from each other, yeah, good luck, God help you. So that's the first line of defense that we utilize. It helps with exposure too, because again, many times you will notice they will have black and white, and exposure matters specifically with ISO. At each ISO, this graph will shift. So for that reason, it has to be taken care of, matching shots. Color space is what you can capture. That's the easiest way to understand. Color space, what you can input, digest. Color gamut is what you can output, as in show to the world. So this TV will have a color gamut. A camera will have a color space. So color space, because we realize our eyes have a lot of capacity. That's awesome. Cameras have a lot of capturing capacity. That's awesome. We do not have display capacity that can truly display. So for example, if data signal says like, this tool supposed to be glowing to, let's say, 300 nits or let's say 2000 nits, again that's within the limits of basically Dolby Vision, but it cannot show that. The display would be like, bro, I'm not designed to go that far. That's why we have the logic of color gamut. Gamut is like a closed enclosed cell inside color space. Color space is there what you are capturing. Enclosed space is color gamut. The reason we did that is like it was very surprisingly smart, so to say. So whenever back in the days, like as early as the Star Wars prequel series, if everything was shot in digital, it still had more colors that you can show at that point in time. The digital file had the colors, so when they needed to showcase it or remaster it for Blu-ray, they could just use that file. It had enough color gamut. The color data was already there. They can master it for 2K or master it for 4K without too much issue. Of course, resolution will not go up that much, but the color would be there, so they can truly master it in HDR. And all the cinema files that you see, digital cinema files that are generally transported in hard drives and DRM'd through satellites, those generally have very high color gamut range, because again, they design in such a way that it's for theater. So they are assuming you have good projector in theaters. So color gamuts. So this is the tool. Color checker is the first tool. That's the easiest way you can make sure at least all the shots within a shot matches. Then we come to the monitor. This is the first thing that you see. Camera saw already what you see. So first thing must be correct. If you mess this part up, you could literally have a model shoot where it's like, model is looking good, it's awesome. You send it to someone and you're like, ew, is she unhealthy? Is she have jaundice? Because again, you messed up the skin tone. And again, we are very sensitive to skin tones. So it's one of those things. It must be correct. Like there is no optional here. It has to be correct. So you have to know which gamut your display is working in. And on top of that, this is where companies are really messing it up, is like, what is the specification of the panel itself? You can literally have two displays, so to say, that you are buying monitors from manufacturers. They're like, both are HDR. One would be super expensive, another would be super cheap. You will like, hey, HDR, super cheap, I'm gonna buy it. Yes, it's not truly HDR because the panel itself is not HDR. So for that reason, if you are actually doing a colorist work, generally it's recommended to have 10-bit. Be mindful, many TVs also, even if they have true HDR certification, true and all that, they may not have a 10-bit panel. They may have an 8-bit panel. So it's one of those things that is really frustrating. You really need to know what is the panel specification if you want to do job critical color work, so to say. And you need external quality control. How else would you know? Like, let's say you show it to someone and they're like, dude, the color does not look right. And they're like, how do you know the color does not look right or his monitor is messed up? If you have external validation as in external quality control. So it has to be a tool that is independent of your monitor, like Snyder or whatever have you, X-Rite. There are many companies that make these things. They are expensive, but well worth their price. Because again, if your work is critical, you have to have this. And it has to be done regularly. This is another painful part, but it has to be. If you are a colorist swap, you will calibrate all your monitors regularly. Many times people do it in every movie. And again, for their certification to be valid, it has to be done yearly. If you delay it more than a year, they are like, bro, our certification, we do not care. Like, you can literally have Sony dealing with basically Dolby Vision and give you a Dolby certified display, and you do not get it calibrated. They're like, dude, I don't know, God help you. Like, they will flat out invalidate its signature, so to say. So it's one of those things. And if you ever wanted to give yourself heart attack, please Google the price of cinema grade colorist display. And these displays are like true HDR displays, so to say. And they are designed, even from early days, even before the HDR craze, they were designed in such a way that they come as close to cinema level display, as in cinema level projection. So they always had like very huge color gamut, so to say. So they are expensive AF, like very, very expensive. Like, if you want to give yourself heart attack, please, I dare you. Then we come to the printout part. Now, unfortunately, I just bought a printer recently, all-in-one, S1 all-in-one, and holy damn. Thankfully, I basically printed a photograph. Again, this is like this is my final photo that I use for calibration and all that. So I had this photo. And again, I took the photo. This is a basically rose photo that literally grew in my backyard. It was awesome. But I was holding it, and just thankfully I looked at my monitor, and monitor was like, bro, these leaves that are here, that's supposed to be green, not supposed to be blackish pink. So I was like, what the hell? Then I paid attention. They were like, no, everything. Basically, that's why I created this image where I have all the four colors. The blue is becoming purple. This color has too much blue into it, and this does not have the yellow warmth that was there when I took this photo. So I had to calibrate a lot of it, and then I finally got something that is how it's supposed to look. So greens are greens, blue are blue rather than violet, and then we have yellow warmth, and the flower color looks more true to life. It was a hell of a hassle. Because I do not have a calibrator, and I don't even know like why this happened to my printer. Many times Epson printer does have this issue where they do not make love properly to your color space data that is coming from your computer, and God help you at that point in time. So that's one of those things. And be realistic about it. Color gamut of basically monitor is less compared to your camera. Color gamut of a paper, basically, this for me is exponentially smaller than your monitor. So if you think 709 is like, oh, it does not have too much color, yeah, come to paper, man. Come to paper. It's very, very small, and you have to take a lot more things into account. For example, the ink. Like, what do you mean by ink? For example, if you have paid attention to many camera companies, you will see printer companies. You're like S Pen, let's say, it's like they have a printer that's like one big black bottle and three color bottles. Then there are photo printers that have one big black bottle and one small black bottle. It's like, what the hell? They will say key color, and then they'll say photo black. It's like, what the hell is key and photo black? Both are black. No, because for economical reason, you ideally want to use pigment as much as possible, but they are idiotically expensive, but they are robust. So for document printing, black printing, so to say, they always use what we call pigment. For colors, you want to use dye. Why? Because dyes have color richness, they blend very well together. So printer have this data where it's like, okay, I'm gonna create the color to best of my ability using dye set. And sometimes if they are printing black, they might just use all three colors, because again, otherwise they have to switch the algorithm. They have to switch the algorithm from dye algorithm to pigment algorithm. Yes, they are different. So that would create an ugly image. So they are like, just overflow the inks. And if you are talking about a photo printer, they are like, no, somebody is actually going to use it for photo, then they have a photo black. And then again, you can see into Canon printers, Epson printer, or whatever have you, generally they have way more color than that. The reason for that is like trying to mix and create that much is just not worth it many times. Just have a dedicated color for it, especially black, that you will see in any printer that is just above basically basic level. You will see photo black. Any printer that is above that, you will also have gray, because again, it's very difficult to create. So they are like, hey, just have a gray color. Pinks, again, necessary for skin tones, so they may have a dedicated color for that. So all of that has to go into account. And then we have to worry about paper. Paper I bought that is like of no name brand versus a paper that is like, let's say, from Kotak or Epson, that will have completely different rendering quality. And each brand and model would be different, as I specified. Epson itself could have like a printer that consumes 4 tanks, consumes 6 tanks, consumes 12 tanks. So it's one of those things that you have to be very mindful. You cannot be like, oh, I know how Epson works. Oh, it's an Epson printer, I'm going to calibrate it, because like, nah. Canon, oh, I know Canon, no. No, you have to calibrate it. Otherwise, you are just running on hope. Be mindful. I have printed photos from this, and again, I paid a lot of money to get like, A4 borderless, and people liked it. It's like, I liked it. It was like, hey, awesome. It's just like happenstance that I was like looking like this, and monitor was there. It's like, whoa, 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 what the hell? It triggered a red alert where it's like, bro, the leaf's supposed to be green, not supposed to be pink. So, and be mindful. Even now, the colors are like almost where I want it, but not precise. And every time I have to print a black and white document, now I have to change it, because now my black and white has extra green into it. So it's one of those things, because if you're not calibrating it, you're running on hope. An art gallery, especially commercial printing, they spend a surprisingly large amount of money, even for newspaper. Why? Because they make their money from color advertisement. Color advertisement has this issue where it's like, let's say, a masala color, like let's say a seasoning on a food, that if the color is a bit off, it will look ugly, as in like, ew. If the color is just right, it's like, so it's one of those things that color is very seriously taken, like, especially if you are dealing with mass production. There's like commercial printing, they do not F around with calibration. They're like, no, get this thing calibrated. So art galleries and all that, commercial printing, they need it. And thankfully, if you're buying a tool that is for a monitor calibration, most of the time, most of the tools also have an ecosystem where you can have a software, you can have a printout, you can put that printout, you can put in there, it can generate a basically IEC profile, you can load it into your Windows and then send all the data. It will be like, I got this. Thankfully, the tools that work on monitor also works on printer. So that's one good thing. And again, you should actually have it if you're really serious about your work. And most companies give you a whole package where they will give you checkers and detectors and all that jazz, and even the software package. So if you buy the right toolkit, you will be like, okay, now I can calibrate my cameras, every lenses, because be mindful, especially if you have different brand lenses. A Sigma lens will be completely different than Tamron lens. You will see it. If you have the checker, then like, whoa. They're completely on the same sensor, they will be different. So now you will know what is my lens signature, and then you can select it effectively. Then you can calibrate your display, and then like, I'm good. Then you can calibrate your printout, I'm really good. So it's one of those things that we have to do this. So this was my presentation. It's like, why the heck we have this hassle of like, printing, calibrating and all that jazz. Hopefully you have liked it, learn from it. In that case, please click the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show me extra disappointment. Please leave a comment, because I do like, do read them all. And subscribe, press the bell icon if you're free. And as always, thanks for watching.